Imagine two children each have a list of favorite stickers arranged in a line. They want to find the longest chain of stickers that appear in the same order in both lines, but the stickers do not have to be next to each other. They can be spaced apart. This chain is called a common subsequence. The longest one is the longest common subsequence, abbreviated LCS. If we try to guess the LCS by checking every possible way to pick stickers, the number of possibilities grows explosively, like trying every combination of letters in 2 sentences. That makes the problem impossible to solve by brute force for anything bigger than a few letters. Dynamic programming, abbreviated DP, helps because it remembers the answers to smaller subproblems, like what is the LCS of the first I letters of the first string and the first J letters of the second string. By reusing these saved answers, we avoid repeating work, turning an otherwise hopeless search into a manageable one. Formally, let x equals x sub 1 x sub 2 x sub m and y equals y sub 1 y sub 2 y sub n be two sequences, strings, arrays, etc. of lengths m and n. A subsequence of x is any sequence x sub I1 x sub I2 x sub ik where 1 less than or equal to I1 less than I2, less than ik, less than or equal to m. A common subsequence of x and y is a sequence that is a subsequence of both. The longest common subsequence problem asks for a common subsequence of maximum possible length. We denote the length of the LCS by LCS of xy. The goal is to compute L equals absolute value of LCS of xy, and optionally retrieve one such subsequence. Explanation: the key to DP is the optimal substructure. The best solution for the whole problem contains optimal solutions for its parts. Consider the last characters of the prefixes we are comparing, x sub I from x and y sub j from y. There are 2 cases. If x sub I equals y sub j, then any LCS of x sub 1 to I and y sub 1 to j must end with this matching character. Therefore, LCS of I, j equals 1 plus LCS of I minus 1, j minus 1. If x sub I is not equal to y sub j, the last character of an optimal subsequence cannot be both of them. So we either drop x sub I or drop y sub j and take the better of the 2 possibilities. Therefore, LCS of I, j equals the maximum of LCS of I minus 1, j and LCS of I, j minus 1. The base cases are LCS of 0, j equals 0 for all j, and LCS of I, 0 equals 0 for all I, because an empty string has no common characters with anything. Explanation: to compute the recurrence efficiently, we build a 2-dimensional table dp0 to m. 0 to n, the entry dp I, j stores the length of the LCS of the first I characters of x and the first j characters of y. We fill the table row by row or column by column, starting from the smallest subproblems, the base cases. For I from 0 to m dp I, 0 equals 0. For j from 0 to n dp0, j equals 0. For I from 1 to m for j from 1 to n if x open bracket I close bracket equals y open bracket j close bracket dp I, j equals dp I minus 1, j minus 1 plus 1 else dp I, j equals max of dp I minus 1, j and dp I, j minus 1. When the loops finish, dp m, n holds the length of the LCS. This bottom-up approach guarantees that when we need dp I minus 1, j minus 1, dp I minus 1, j, or dp I, j minus 1, they have already been computed. The full table uses big O of m and memory, which can be large. 2 common tricks cut the memory down. Rolling arrays. Observe that to compute row I, we only need row I minus 1. So we keep just 2 one-dimensional arrays of size n plus 1 and overwrite them alternately. This reduces space to big O of n. Hirschberg's algorithm. It uses a divide and conquer idea together with the rolling array dp. First, we split x in half, compute LCS lengths for the left half against all of y forward, and for the right half against all of y backward. The point where the sum of these 2 lengths is maximal tells us where the optimal LCS splits and why we then recurse on the 2 halves. Hirschberg's method uses only big O of n space while still returning the whole LCS, not just its length. Having the length is useful, but often we need the actual sequence of characters. Starting from dp of m, n, we walk backwards. If x sub I equals y sub j, then this character belongs to the LCS. Prepend it to the answer and move diagonally to I-1, j-1. If they differ, we follow the larger of dp of I-1, j and dp of I, j-1. If they are equal, we can pick either branch. Any choice yields a valid LCS. We repeat until we reach a cell in the first row or column. When we use the rolling array version, we cannot keep the whole table, so we reconstruct by using Hirschberg's recursive splitting. Each recursion returns the LCS for its subproblem, and the concatenation of the two halves gives the final LCS. This works because the algorithm already determines where the split occurs. The nested loops run m times n iterations, each doing constant work, so the running time is theta of mn in the worst case. This is also the average case because every cell is visited regardless of the input strings. Memory-wise, the naive table needs big O of mn cells. Using rolling arrays cuts it to big O of min of m, and n. Hirschberg's algorithm also uses big O of min of m and n space, while still giving the full LCS, at the cost of a slightly higher constant factor due to the recursive calls. If the alphabet is small, for example DNA with only 4 letters, there are more advanced tricks, like the 4 Russian technique, that can improve the time to big O of mn divided by log n. But the classic DP is the most widely taught and understood solution. LCS is the backbone of many real-world tools. Edit distance, the minimum number of insertions, deletions, and substitutions to turn one string into another, can be expressed using LCS, because deletions and insertions correspond to characters not in the LCS. Diff utilities, programs like git diff, highlight differences between two files by finding their LCS. The unchanged lines form the LCS, while the remaining lines are shown as additions or deletions. Bioinformatics, comparing DNA or protein sequences, often starts with LCS or its weighted variants to discover common motifs. Constrained LCS. Sometimes extra rules are added, such as the subsequence must contain a given pattern or the distance between consecutive matched characters cannot exceed k. These lead to modified DP recurrences, but the same core idea of building a table of optimal subproblem solutions. All these applications rely on the same principle: break a big problem into tiny overlapping pieces, solve each piece once, and combine the answers.